All right, so let's look at the contact lens question. So they're asking you, this is here, the energy transfer from the anterior chamber of the eye through the cornea varies considerably depending on whether a contact lens is worn. Treat the eye as a spherical system, assume the system to be steady state, and then they say the cornea and the lens cover 1/3 of a spherical surface area. So that's kind of a hint. Basically, they're trying to tell you to approximate the eye as 1/3 of a sphere. So they give you the various parameters. They want you to construct the circuit with the contact lens and then without the contact lens. So, and then they say, discuss the results. Do you lose more heat with the contact lens or without the contact lens? So I have the circuit over here. Basically, in the inner eye, from the anterior chamber to the inner surface of the cornea, they approximate it as a fluid, basically. They also approximated that right at the very center of the eye, we have a constant temperature. That's basically that T infinity I. So that's going to be the battery. So from there to the inner surface of the cornea, there's going to be thermal resistance due to convection, because we're treating it like a fluid. So that's going to be a convection thermal resistance, which looks like this. If you're wondering what this comes from, here's some good news. The convection thermal resistance is always going to be 1/HA, regardless of the coordinate system. Doesn't matter coordinate system, 1/HA is the thermal resistance due to convection. So the only thing that changes for coordinate systems is just the surface area. So for a sphere, right, your surface area would be 4 pi r squared, but now we're approximating the eye as 1/3 of a sphere, so you just got to divide that surface area by 3, hence this. So for the inside of the eye, we have that convection thermal resistance, and also we'll have it on the outside, thermal resistance due to convection. Okay, the conduction thermal resistances are through the cornea and then also through the contact lens when we're solving with the contact lens on. So if you're wondering where these come from, I'm gonna explain that. So that's basically the circuit with the contact lens. Now, when you do the circuit without the contact lens, basically you're removing the thermal resistance due to conduction from the contact lens. Now, you have to be careful though, because when you remove this contact lens, your thermal resistance due to convection from here out changes, right? Thermal resistance due to convection from here to here is dependent on the surface area. So with the contact lens, your surface area is this, right? It's basically this radius, from this radius. So it's 4/3 pi r sub 3 squared, right? But when you take the contact lens out, now it's just the outer part of the cornea is exposed to the environment. So now your radius has gone down, hence this area actually decreases. So it changes. It's not going to be radius 3 anymore. It's going to be now radius 2. So that's the only thing you have to be careful of. Now, let's talk about where I got this thermal resistance. So basically, you need to look at Fourier's law. That's where it comes from. So in one section, we were able to get to this part. In the other section, we haven't gotten to it yet, but we will get to it next week. So for a sphere, so Fourier's law is pretty much the same. It's just minus Ka. Then you take derivative dt dr, right? So instead of, normally we used to write it with dx, but now it's dr because we're in cylindrical coordinates and heat transfer is in the r direction, right? Whereas previously we were in Cartesian coordinates and we assumed heat transfer only in the x direction. So it's pretty much a similar shape of the Fourier's law. So now all we have to do is put in the area, the surface area, right? So for a sphere, it's just 4 pi r squared. That's your surface area. So basically, if you were just looking for the thermal resistance for a spherical system, you would just go from here onward with the proof. But in our problem, we actually have to derive it again because we need to do it for 1/3 of a sphere. It's the same proof. It's just there's going to be a factor of 1/3. Where is that going to be? Here, right? Because your surface area is now not a full sphere, it's 1/3. So we're going to have to basically divide by 3 over here. So basically, it's the same thing. You know, you have the minus Ka, right? But now the area, the surface area, is going to have that 1/3 there. So we have here 4 pi r squared, but then we divide by the 3. And now you would just continue with the proof like you normally would to find the thermal resistance. So basically it's going to involve separation of variables. Everything that has r in it, I'm going to move it to the left-hand side. So we're going to get here 3 times q over 4 pi r squared dr. On the right-hand side, we're going to leave the minus k dt, like so. And then we're going to integrate both sides. My integral sign, there. That's better. All right. So we're going to just integrate between two random radii from R1, let's say, to R2. We're going to just assume a typical like general sphere. So imagine you have a sphere like this and pretend that, you know, the sphere inside is, you know, has some fluid. So from here to here would be R1. And then from here to here would be R2. So basically we're integrating from this region to this region. Okay, you could make R1 0 if you wanted. If this is not hollow, you could make R1 0. But for the sake of keeping things as general as possible, I'll make it R1. So on the right-hand side, we're going to integrate from the temperature at that R1, which we'll call TS1, and we'll integrate to a temperature TS2, okay, which is the temperature at R2. So on the right-hand side, let's take out the constants. We'll do the easy part, 3q over 4 pi. And then we're going to integrate, you know, the dr over r squared between the limits r1 and r2. Here the k we assume to be constant comes out, and this integral is just going to be ts2 minus ts1. The integral on the right-hand side, right, you can imagine the 1 over r squared. It's basically r to the minus 2. So when you add 1, it's going to be r to the minus 1, okay, which is basically 1 over r. But then you have to remember that you got to divide by that exponent, so you have a minus 1 overall factor that sort of that comes in. So here is your left-hand side, and we're going to evaluate that. Evaluate this integral from R1 to R2. On the right-hand side, we get the minus k, like this. So, okay. So let's evaluate. Here I'm going to have minus 1 over R2. Minus minus is plus, so I get plus 1 over R1. And here I'm going to take this minus sign and put it in the parentheses. So I get here TS1 minus TS2. Okay, when you take the minus sign, you can switch them into parentheses. All right, I'm going to write this one more time down, and in fact, I'm going to just solve for Q. If I solve for Q, and let me, perhaps, I need another, let me move this away. It's kind of in my way right now. So I'm going to get here 4 pi k over 3. That whole 1 over r, right, that whole thing, I'm just going to write it the proper way. In other words, 1 over r1 minus 1 over r2. Okay. Right, because it's a 1 over because you got to divide by it. And you're going to have here the TS1 minus TS2. This portion over here is like your voltage. This portion over here is like your current. And then this portion basically is like 1 over the resistance. So basically from here, we can get our thermal resistance for 1/3 of a sphere. Okay, so the thermal resistance, let's write it out, is basically, it's the reciprocal, so you're gonna have 3 over 4 pi k, and then that stuff in the brackets basically finds its way into the numerator like so. Okay, notice that in this entire discussion, R1 we assume to be the smaller radius, R2 we assume to be the larger radius, right? And this works out in such a way that your thermal resistance is not going to be negative, right? Your thermal resistance cannot be negative. So you have to be careful, basically, right? So the thing that could be negative is potentially this, right? Which will make Q negative, but thermal resistance is supposed to be a positive number. So that's why I derived it in this way. So that's basically where this comes from. So if you go back over here, let's go to this one, which has the contact lens, right? That's where it's exactly the same thing, right? We're integrating from the smaller, in other words, R1 is the smaller radius, R2 is the larger radius, right? So we're finding heat transfer from here to here by conduction, okay? Then for the contact lens, it's R2 to R3, right? But you still got this factor of 3 that's hovering over there. So that's basically how you would set it up. The rest of it is just going to be regular algebra and math, okay?